Picture yourself walking a hilly trail. You climb, then the ground levels off at the top of a rise. You head into a dip, and at the bottom it goes flat again. Those flat moments, the very top, the very bottom, are special. The derivative is the slope of the trail, how steep it is right where you stand. Watch a straight edge glide along, tilting to match. Uphill it leans one way, downhill the other. But at the top of the hill and the bottom of the dip, it lies flat. Flat means the slope is exactly zero. A spot where the derivative hits zero has a name, a critical point. Every peak and valley hides at one. So to find them, you hunt for where the slope goes flat. Let's pin this down precisely. A critical point is an input. See, where one of two things happens. Either the derivative there is zero, or the derivative doesn't exist. The curve passes through, but has no well-defined slope there, like a sharp corner or a cusp. Either way, C is a critical point, provided the function is defined there. Two flavors. On the left, a smooth peak where the slope is exactly zero. The tangent lies flat. When the derivative is zero, we also call it a stationary point. The function pauses, going neither up nor down. On the right, a sharp corner. The graph is unbroken, but the slope jumps. No single tangent, so the derivative doesn't exist. That too is a critical point. Both kinds are candidates for a peak or a valley. Here's the payoff idea of the whole lesson. The sign of the slope tells you the shape of the curve. Let me paint it onto the graph. Wherever the slope is positive, the derivative above zero, the trail is climbing. I'll color every rising stretch green. The function is increasing. Wherever the slope is negative, the trail is falling. I'll color that rose. The function is decreasing. Green up, rose down. The slope sign is the direction of the curve, and notice where the colors switch. Green turns to rose at the peak, and rose back to green at the valley, exactly at the flat spots, where the slope passes through zero. The critical points are the seams between rising and falling. To do this by hand, without drawing the whole curve, we use a tool called a sign chart, just a number line for the derivative. Let's build one where the derivative factors into x plus 1 times x minus 1. The derivative is 0 when either factor is 0, at x equals minus 1 and x equals plus 1. Those are our critical points, and they chop the number line into 3 intervals. Here's the line, the two critical points marked in gold. 3 intervals, left of minus 1, the middle, and right of 1. In the left interval, test minus 2. Minus 1 times minus 3 is positive. The derivative is positive, the function increasing. Mark a plus. In the middle, test 0. 1 times minus 1 is negative, decreasing. Mark a minus in it. And on the right, test 2, 3 times 1, positive again, increasing, a plus. 1 test point per interval is all it takes. Read the finished chart straight off. Plus, minus plus, increasing, decreasing, increasing. Without ever plotting the curve, the sign chart hands us the whole up and down story. That sign chart does more than describe the shape. It classifies every critical point. This is the first derivative test. Look at how the sign of the derivative changes as you cross the point. First case. If the derivative goes from positive to negative, climbing, then falling, the curve rises to the point and drops away after. That's a peak. A local maximum. Second case. If it goes from negative to positive, falling, then climbing, the curve dips to the point and rises out of it. A valley. A local minimum. And the case people miss. If the sign does not change, positive on both sides or negative on both, it is neither a max nor a min. The curve flattens for an instant and carries on. A plateau. Now the derivative of the derivative, the second derivative, tells you which way the curve bends. This is concavity, and it's all about where the tangent sits relative to the curve. When the second derivative is positive, the curve is concave, up. It holds water like a ball. Draw a tangent, and the curve sits above it, curling upward. When it's negative, the curve is concave down, an upside-down dome. Now the curve sits below its tangent, bending downward. Ball versus dome, concave up versus concave down. And the moment concavity flips from bending down to bending up is called an inflection point. Here's a curve that cups downward on the left, in rows, then upward on the right, in blue. Right where they meet, the bending reverses. At an inflection point, the second derivative is 0 and changes sign. The curve straightens for an instant, then curves the opposite way. Concavity gives a second, often faster way to classify a critical point. The second derivative test. Suppose you found a stationary point, where the first derivative is 0. Just check the concavity there. If the second derivative there is positive, the curve is a ball, a local minimum, sitting at the bottom of an upward curl. If the second derivative is negative, the curve is a dome there, a local maximum, sitting at the top of a downward curl. But if the second derivative is also 0, the test says nothing, inconclusive. The point could be a max, a min, or neither. When that happens, fall back on the first derivative test and check the sign change. Let's put every piece together on one function. The cubic x cubed minus 3x. We'll find its critical points, classify them, and draw it to confirm. Differentiate. 3x squared minus 3, which factors as 3 times x minus 1 times x plus 1. Set it to 0. The critical points are x equals minus 1 and x equals plus 1. The two places the slope goes flat. Build the sign chart from 3x squared minus 3. At minus 2, the derivative is 9, positive, increasing. At 0, minus 3, negative, decreasing. At 2, 9 again, positive, increasing. So plus, minus, plus. At minus 1, the slope goes from positive to negative, a local maximum. At plus 1, it goes negative to positive, a local minimum. The first derivative test, straight off the chart. Cross-check with the second derivative, 6x. At minus 1, it's minus 6, negative. Concave down, confirming the maximum. The height? Minus 1 plus 3 is 2. The peak is at minus 1, 2. At plus 1, it's 6. Positive, concave up, confirming the minimum. The height? 1 minus 3 is minus 2. The valley is at 1, minus 2. And 6x is 0 at x equals 0, where it flips negative to positive. So the origin is an inflection point. Now let's draw the curve and see it all. There it is. Rising green up to the peak at minus 1, 2. Then falling rows down through the origin to the valley at 1, minus 2. Then rising green again, the peak, the valley, and the inflection at the origin. Every prediction from the derivatives sitting right there on the curve. The maximum higher than the minimum, exactly as the numbers said. Your turn. Take x cubed minus 12x. Find its critical points and classify each one with the second derivative test. Pause the video, work it through. Then come back and check. The derivative is 3x squared minus 12, which factors as 3 times x minus 2 times x plus 2. So the critical points are x equals minus 2 and x equals plus 2. The second derivative is 6x. At minus 2, it's minus 12, negative, a local maximum. At plus 2, it's 12, positive, a local minimum. Plug in the values. F of minus 2 is minus 8 plus 24, 16. The maximum at minus 2, 16. And f of 2 is 8 minus 24, minus 16. If your peak and valley match those, you've got it. Before the recap, the traps that catch people, and the first is the big one. The slope being zero does not guarantee a peak or a valley. Look at x cubed. Its derivative, 3x squared, is zero at the origin, a critical point, tangent flat. But 3x squared is never negative. The slope is positive on both sides. No sign change. So the curve climbs right through, an inflection, not an extremum. Necessary, but never sufficient. So trap 1, restated, a zero slope is only a candidate. Always check whether the derivative actually changes sign across it. Trap 2, hunting only where the derivative is zero. Critical points also live where the derivative is undefined. Corners and cusps. Miss those, and you can miss a genuine minimum. Trap 3, trusting the second derivative test when the second derivative is zero. It tells you nothing there. Go back to the sign of the first derivative. And trap 4, confusing local with global. A local maximum is only the highest point nearby. Somewhere else, the function may climb higher still. Local is what these tests find. The global picture is the next lesson. Let's lock it in. Critical points are where the derivative is zero or undefined. The only places, along with endpoints, a local peak or valley can hide. The sign of the first derivative gives the shape. Positive means rising, negative means falling. The first derivative test classifies each by its sign change. +2 minus is a maximum. -2 plus a minimum. No change neither. And the second derivative test is the quick check. Positive concavity means a minimum, negative a maximum. Zero means fall back to the first test. Master these, and you can read the whole shape of a curve from its slopes.